In developing the relation of electromagnetic wave propagation to familiar electromagnetic principles, we begin with a particularly simple and somewhat artificial example of an electromagnetic wave. We first postulate a particular configuration of fields and then test whether it is consistent with the principles mentioned previously, particularly Faraday's law and Ampere's law, including displacement current. Using an XYZ coordinate system as shown in figure A, we imagine that all space is divided into two regions by a plane perpendicular to the x-axis, this plane here. At all points to the left of this plane, all of these points, there is a uniform electric field capital E in the y direction and a uniform magnetic field B in the z direction. So you've got E in the y direction and B in the z direction. Furthermore, we suppose that the boundary surface, which may also be called the wavefront, this area here, moves to the right with a constant speed c, as yet unknown. We are going to find what the speed of c is. Thus the E and the B fields travel to the right into previously field-free regions with a definite speed. The situation, in short, describes a rudimentary electromagnetic wave, provided that it is consistent with the laws of electromagnetism. Here we are not going to worry about how such a field configuration might actually be produced. Instead, we simply ask whether it is consistent with the laws of electrodynamics, that is, with Maxwell's equations. First, we apply Faraday's law to a rectangle in the xy plane. The rectangle is located so that at some instant the wavefront has progressed part way through it, as shown. Remember that E dot dl, that's the electric field all around the perimeter, that's a line integral. In a time delta t, the boundary surface moves a distance c delta t to the right, sweeping out an area AC delta t of the rectangle. In this time, the magnetic flux increases by B times AC dt, and that's, so you can see this B is, the magnetic flux is going in this direction. We get a magnetic flux for that area. We take the vector area element to point in the z direction, so this is a positive quantity. The rate of change of magnetic flux is given by d flux by dt equals BAC. Now, according to Faraday's law, this expression must equal the negative of the line integral, evaluated counterclockwise around the boundary of the area. The field at the right end, so this right end, that's going to be 0. Okay, there's no field on that right end because there's nothing there. And the top and bottom sides do not contribute because the component of E along dl is 0. In other words, there's going to be nothing at the top or the bottom here, because when you're going in that direction there's no component in the E direction, yeah, so they just add to 0. So the right side and the bottom and the top all add to 0. So the only one that contributes is when we've gone all the way around. Now we're going down and we're going opposite the E, so we're going down opposite the direction of the E field, so that becomes minus EA because we've gone against the field there. Using Faraday's law, we've got that equals this, in other words BAC equals EA. Because of the minus sign here in Faraday's law, the minus signs cancel and we end up with E equals CB. The wave we have postulated is consistent with Faraday's law only if the electric field, the magnetic field and C are related, as in equation 1, E equals CB. So next we can apply Ampere's law to a rectangle in the XZ plane. There is no conduction current, so IC equals 0, so we're using Ampere's law, but there's no conduction current because we're in space here, so that's equal to 0. In terms of electric flux, Ampere's law with displacement current but no conduction current is just this now. So in figure C here, we take the vector area to point in the y direction. If that's the positive direction, then we're going to work our way round this direction. Looking at this side and this side, you can see that they're perpendicular, so there's going to be no contribution there, so those two sides are 0. And again on this side, because we're in empty space as the wave front moves forward, there's nothing on this side either. So those three sides are going to be 0. So the only side again is going to be when we come back towards the direction, and this time we're going in the same direction as the B field. Just repeat that in my notes. We take the vector area to point in the plus y direction so that the electric flux is positive and increasing. The line integral is then evaluated counterclockwise around the boundary of the curve. The change in the electric flux in time dt is the area BC dt swept out by the wavefront multiplied by E. In evaluating the line integral of B, we know that B is 0 on the right end of the rectangle and is perpendicular to the boundary on the front and back sides. Thus only the left end, where B and dl are parallel, contributes to the integral, and we find that B dot dl equals BD. Combining these results of equation 2 and dividing out the common factor, the B part, we end up with BD equals U naught epsilon naught E BC, and then the B's cancel, and we end up with B equals epsilon naught permeability naught C E. So rewriting 5 as, and we can bring the E to one side, we end up with 1 E to the naught U naught C B. This equation here and this equation, remember we've got a term now in E and a term now in E. Now 1 and 6 must be equal, so that can only be true if we set these two terms now equal, then we end up with C equals 1 over epsilon naught U naught C. And then solving for C, we end up with C equals 1 over the square root of epsilon naught mu naught. When you actually plug in the permeability of a vacuum and the permeability constants, if you plug those values in, you find that C equals 3 times 10 to the 8 meters per second. The postulated field configuration is consistent with the laws of electrodynamics, provided the wave moves with the speed given above, which of course is recognized as the speed of light, 3 times 10 to the 8 meters per second. We have chosen a particularly simple way for study in order to avoid undue mathematical complexity, but this special case nevertheless illustrates several important features of an electromagnetic waves. 1. The wave is transverse. Both the electric field E and the magnetic field B are perpendicular to the direction of propagation of the wave and to each other. 2. There is a definite ratio between the magnitudes of the electric field and the magnetic field. And 3. The wave travels in a vacuum with a definite and unchanging speed. It is not difficult to generalize this discussion to a more realistic situation. Suppose we have several wavefronts in the form of parallel planes, perpendicular to the x-axis and all moving to the right with speed c. And suppose that within a single region between two planes, the electric and magnetic fields are the same at all points in the region, but that they differ from region to region. An extension of the development above shows that such a situation is also consistent with Ampere's and Faraday's laws, provided the wavefronts all move with the same speed c, given by this equation here. From this picture, it is only a short additional step to a wave picture in which the electric and magnetic fields at any instant vary smoothly rather than in step as we move along the x-axis, and the entire field pattern moves to the right with speed c. Later we will consider waves in which the dependence of the electric and magnetic field on position and time is sinusoidal, but first we consider the energy associated with the electromagnetic wave.